So in all honesty, I don't have a lot of experience with conics in polar form. Conic sections, yes. Polar equations or polar forms for graphing, totally. But putting it together is something I've just never really done. I'm not entirely sure why. I went through an entire math degree at university, and we never really touched on this ever. But now that I've had a chance to work with them a little bit, it turns out they're really cool. And like all things math, way more fun than you think it's going to be before you actually jump in. So, two things that we have to learn or discuss. First, we have to talk about eccentricity. And I don't mean my own personal foibles. Conic sections have eccentricities. And we need to develop the general forms of the equations for conic sections, just like conics in rectangular coordinates each have their own sort of form or alteration on the same theme. So too do polar forms. So let's start with eccentricity, and to show it, I'm going to start with just a free-floating ellipse. And remember, ellipses have foci. There are two. I'm just going to use one. We'll focus on one. Ha ha, little pun. And they have a directrix. All right. And so I have a radius, which would be the line segment connecting the point F for the focus and the point P for a point on the ellipse, and then a line segment that connects P to Q, where P is the same point on the surface or the edge of the ellipse, and Q is a point on the directrix. So the eccentricity of a polar conic is E, the letter E for eccentricity. It's a ratio between these two line segments. So the ratio is PF over PQ. And this is a constant. So if I decided to use a different FP to Q, the ratio would be the same. The length of each of the line segments is different, but the ratio between those two would be consistent or constant for the entire conic, excuse me, conic section. So E is the eccentricity of the conic, and in this form, it's called the constant ratio. So E is written in this form as a constant ratio. And if I were to solve for PF, I would get the form called the constant multiplier, or E as a constant multiplier. All right, so we're going to do that. PF equals E times PQ, and we're going to evaluate this form to find our equation for conics in polar form. So let's start with the left-hand side, which we want to write in rectangular coordinates, meaning we want to use x's and y's to describe PF. Well, PF is a distance, and if I had a Cartesian plane, I would identify x and y values for both of these, and I'd be able to write the distance between them using the distance formula as the distance is the square root of x squared plus y squared. Easy peasy. E, I don't want to do anything with. PQ, what would be the way to write PQ? Well, if this were a Cartesian plane and I had the origin here, I would be able to identify the length of PQ as the directrix, which equals D, the location of the directrix on the x-axis minus whatever the x variable is. In each case, I have an x value. So this would be E times the directrix minus x. Okay, now I'm going to do a bunch of calculations to convert. You'll recognize them. They're not necessarily intuitive, but they'll take us right where we want to go. First things first, we're trying to get everything into polar form. So this would represent our radius in polar form. So I can write that as r. The left-hand side is done. So the radius equals e, still not wanting to deal with that yet, times, well, how would I convert? Well, d is just a value, minus, how could I convert x into polar form? Well, we know exactly what that is. That's r cosine theta. Okay. Next, I want to distribute the e. Can you hear the traffic outside? It's our first really, really warm day of the summer, and so I have to have the door open, and apparently everyone is going for a drive in the sunshine, so hopefully it's not too loud. So I have ED minus ER cos theta. Now I want to add ER cos theta to the left-hand side, so R plus ER cos theta equals ED. Factor the R out. Hang on, got myself a little lost. That's some bad notation. I'm thinking about the sounds outside and wishing I was out there. So R times 1 plus, I'm focused now, E cos theta equals ED. And now I'm going to divide by 1 plus E cos theta. So R equals ED over 1 plus E cosine theta. So for the major axis, horizontal major axis, this would be the formula I would work with. I could have done exactly the same thing. I could have drawn an ellipse that was squished on the y-axis, and then the only thing that would be different is my cosine would be a sine because I'd be dealing with the y-axis. So this is the formula for this picture having been derived. I'm going to write the general formula. This is my own way of writing. R equals ED over 1 plus or minus, it could be a positive or a negative, E times, and this I'm going to write trig theta. And there's only one reason for that. And at fair warning, this is my own special notation, so sometimes a future teacher will say, what the heck are you doing? Just be prepared. I happen to like this notation because it lets me memorize one formula and then use logic and reason to tell me how to read all the other types, rather than memorizing 4 formulas with different things going on in them. So here's how we break it down. First things first, E is going to tell us what type of conic we're working with. When we have E, when we have the formula written in this form, E will say whether we're dealing with an ellipse, a parabola, or a hyperbola. And here's how. If E is less than 1, but greater than 0, greater than 0 makes sense because these are distances, they couldn't be negative, and then less than 1, then we know that we're dealing with an ellipse. If E is equal to 1, then we're dealing with a parabola. And if E is greater than 1, then we're dealing with a hyperbola. Okay, those are the only choices, and that's how we can tell. Now, do we have a major axis or a minor axis ellipse? So this would be major axis on the x-axis, but I could have had an ellipse that squeezed this way with a major axis on the vertical or y-axis. How do we tell? Well, thank you for asking. Luckily I know. If it's a cosine theta, so if our trig value is cosine, then we know that we're dealing with the vertices on the x-axis. And that's pretty easy to remember because even here we used cosine to convert from a rectangular coordinate x to a polar coordinate cosine theta. So the vertices would be on the x-axis, and that would look like, for an ellipse, something like that, or they would be horizontal to the x-axis, not necessarily right on it, but the vertices would be on a line horizontal to the x-axis. If it were a parabola, it would go like that. And if it were a hyperbola, the vertices would be on the horizontal or a horizontal line. If the trig function is sine theta, you guessed it, the vertices would be on the y-axis or parallel to the y-axis. I'm going to say on the y-axis because that's how I remember it. I guess I could say along. Let's go ahead and say that. Well, let's say parallel to the y-axis. I guess that was just as easy, wasn't it? So parallel to the x-axis or parallel to the y-axis. That means I would have an ellipse that was longer, skinny and tall. I would have a parabola maybe here, and I would have a hyperbola that looks like this. Vertices on the y-axis. So the last piece of information will be taking d and the plus minus together and using it with our sine and cosine. If d is positive, if it's a cosine, major axis, or vertices on the horizontal axis or a horizontal line, then d with the plus or minus tells us that the directrix is at x equals d or x equals minus d, depending on the sign, and it's the same sign. Or it would be at y equals d or y equals minus d. And the effect of that, in the case of the parabola, would be to tell you, is your parabola downward facing or upward facing? Is your parabola to the right or left? Does your ellipse lean to the left or lean to the right? And that's information you would get from d and the sign in the formula. All right, so let's do an example. R equals, I want to evaluate and sketch the graph of R equals negative 15 over 6 sine theta minus 3. So the first thing I notice is that in my form, my trig form, I have my constant in front, plus or minus e trig theta, and this is backward. So I'm going to rewrite that real quick. And then I notice that I don't have a 1 in front. It's critical that I have a 1 in the front. So I could factor out a negative 3 and then cancel with the numerator, but I notice that everything sort of cancels by 3. So I'm just going to do it in one step. So negative 15 divided by 3 is 5. Negative 3 divided by negative 3 is 1. And positive 6 divided by negative 3 is minus 2 sine theta. So that means I have this value here, my eccentricity, which tells me that E is greater than 1. Therefore, I'm looking at a hyperbola. And because it's a sine function, it has vertices, let's say that way, on a vertical axis. And d is buried in this numerator. ED equals 5, so I know ED, but d is negative, equals 5. But E is 2, right there, E is 2. So 2 times negative d equals 5. So negative d equals 5 halves. So d equals negative 5 halves. So now I know, if I want to sketch this out, is that there is a horizontal directrix where d equals negative 5 halves. I know that I'm going to have one arm of my hyperbola between 0. By the way, all of these, I don't think I said this explicitly before, these formulas, this formula always has the focus at 1, or at the origin. We'll look in a little while at shifting those off using H and K translations, but right now the general formula always has a focus at 0, 0. So I know that I have a branch of my hyperbola that is with the vertex between the focus and the directrix, and another branch somewhere on the other side of the directrix. So if I want to know critical values in this case, for example, if I want to know what this point is, or this point, or this point, I can use polar evaluations and notice that this would be theta equals 0. So I could go back to r equals negative 15 over, well, I probably don't want to use that form, do I? This one's so much easier. R equals 5 over 1 minus 2 times the sine of 0, which equals 0. So that would be 5 over 1, which is 5. And so this point is 5. Now, let's look for the vertex. R equals 5 over 1 minus 2 times the sine of 3 pi over 2 is negative 1 equals 5 over 1 plus 2 is 3 5/3. Now that's a little disconcerting because look, I'm on the negative y-axis and I have a positive 5/3. But remember, we're not talking about, I've sketched it here with an x and a y, but we're actually talking about polar axes. So the truth is, at pi over 2, if this were a circle, say, excuse me, at 3 pi over 2, if this were a circle, I'm looking for all the radius points. And so the radius is definitely going to be a positive value. And the radius here would obviously be a positive value and a positive value. And on this side, the radius would also be a positive value because you're using polar graphs with a polar axis, an angle, or polar coordinates. So let's prove that by finding the value for this point. So if I'm going to pi, r equals 5 over 1 minus 2 times the sine of pi is 0, which equals 5 over 1 minus 0 is 1, which equals 5. I get a positive value out of the equation, and that makes total sense because these are polar graphing. Using a polar graph would give me a positive value.